Hello and welcome to the first video on the Boolean Logic, Algebra and Circuits playlist. These videos cover the unit that we refer to in the classroom as Unit 8, the Boolean Algebra topic. So in this video we're going to introduce the way in which we tend to articulate Boolean logic at A level using words such as to illustrate, derive and simplify. We're going to explore the difference between the GCSE Computer Science and the A-level Computer Science spec with regard specifically to Boolean logic, and we're going to introduce the XOR gate or exclusive OR gate, and to introduce some primitive Boolean expressions which use some mathematical symbols and terminology that will be new to you. Okay, so let's start off by looking at the big difference between GCSE Computer Science and A-level Computer Science when it comes to Boolean logic. In the classroom I will provide you with the specific pages that relate to the learning for Boolean Algebra and Boolean Logic from the OCR specification PDF, but I thought it would be quite useful in this video to have more of a pictorial view of the big difference between the two, and for you guys to understand the scope of what's required at A level. So at GCSE Computer Science, our view or the learning that's required when it comes to Boolean logic is actually quite restricted, which was nice when you were a GCSE Computer Science. There wasn't too much to take on board when it came to the Boolean logic topic. And if you remember, you were expected to be able to illustrate Boolean logic with 3 logic gates, and that would have been the OR gate, the AND gate and the NOT gate, and to be able to work with their associated truth tables as well. You were also expected to be able to derive a truth table from Boolean logic illustrated with a limited number of logic gates, and to be able to illustrate Boolean logic by deriving a truth table from a limited number of logic gates. And you can see below a typical GCSE style example where 3 logic gates have been included in a circuit, and you're asked to complete the truth table that describes that circuit. So if you're wondering why it is I'm using quite a convoluted language here with derive and illustrate, for example, well, this is the way that we tend to think about and talk about to articulate the relationship between logic gates and truth tables and Boolean logic in general. In fact, at A level you'll begin to appreciate that truth tables and logic gates are one of the ways which we illustrate Boolean logic, the bigger topic of Boolean logic, and you'll get a sense of what that looks like a little bit later on in this video. So let's deal with the little differences between GCSE Computer Science and A-level Computer Science with regards to Boolean logic. The first thing that we need to do is to extend the GCSE scope of learning to include an extra logic gate, which is the exclusive OR gate, and for you guys to be aware of the terms NAND and NOR gates. So that's a small extension to the type of learning that you were doing at GCSE. In addition, we need to extend the GCSE scope of learning to include basic mathematical or Boolean expressions that describe each of our logic gates. You can see the screen's beginning to fill up with question marks, and those gaps will obviously be filled a little bit later on in this and future videos on the playlist. So for each of our primitive logic gates, the OR gates, the AND, the NOT and the exclusive OR gate, there is a mathematical expression that we can also use to describe the logic of each of those gates. Okay, so we're beginning to extend the learning now, and we're beginning to get into real A-level country, because the third thing that we need to do for you guys is to introduce a new way to illustrate Boolean logic, which is called the Carnot map. We are going to be using Carnot maps a lot during this topic. So in addition to the truth table and the symbols that you guys have come to know and love for the OR gate, AND gate and NOT gate, there is a third way in which we can illustrate the logic of each of these gates, and that's the Carnot map. So at GCSE you learnt how to express logic with rudimentary circuits, a maximum of 3 logic gates joined together, which you saw on a previous slide, and the truth table associated with that simple circuit. But at GCSE we didn't really learn about useful circuits which are used in everyday digital devices. Now at A-level we introduce commonly used digital solutions. We only need to learn about 2, which is the adder and the flip-flop, and those are just 2 of the bread and butter applications of Boolean logic manufactured for real-world digital circuits. So this penultimate slide is essentially saying that the biggest gap, the biggest jump that you will need to make from GCSE Computer Science to A-level when it comes to Boolean logic is the need to learn and to apply Boolean algebra. Yes guys, we need to do quite a bit of maths to support this unit, and in fact Boolean algebra is the overarching concept that you need to learn for Unit 8, which essentially covers everything else that you learn for this particular unit. So at A-level you will need to understand and to apply the mathematical rules and theorems of Boolean algebra in order to derive simplified mathematical expressions, and then you'll need to illustrate those mathematical expressions using logic gates and truth tables. You'll also need to do the same thing in reverse as well. Karnaugh maps, which I mentioned in one of the earlier slides, are also a very important tool used to derive simplified Boolean expressions. You will be using some of the techniques and skills learnt from GCSE maths, and certainly if you are a student of A-level maths you will be confident learning and then applying the type of maths needed for computer science at A-level. So just to give you a taster of this, some of the concepts and techniques that you will have come across at GCSE maths, such as simplifying expressions, factorizing, finding the common term, and at A-level doing variable substitution, so substituting an expression for a variable and then substituting it back out at the end of your mathematical steps to make the maths easier, are things, concepts, tools that we will be applying when we learn and use Boolean algebra. Okay, so before I finish with this slide, I'm just going to wrap up with one final point, and I'm sure you guys have come to the same conclusion as well, which is practice, practice, practice. This is a unit on your A-level computer science course which is very heavily dependent on practicing maths skills and maths learning. Some of those you will have picked up at GCSE maths, others will be new, but it is really, really important to practice Boolean algebra as much as you can, and even to revisit this unit yourself in your independent study time and just go, right, so we haven't done Boolean algebra for a while, I'm just going to practice and revisit those tools and techniques, because if you don't do that they get rusty very quickly. So to support you guys, I put together a number of packs which are essentially past exam paper questions which are specifically to do with Boolean logic, algebra, flip-flops and adders. I've actually gone through each of those questions myself and given you the worked examples of how to get from the question to the correct solution. Those are available for you. I will give those to you in the classroom. Please do take the opportunity to go through those yourself if it's not part of your homework or independent study from me, and make sure you give yourself every opportunity to practice Boolean algebra. Very nice questions to have in a mock exam or final, but you do need to make sure you've practiced them and you are really confident tackling those types of questions. So that brings me to the end of the first part of this video. We've covered off bullet points 1 and 2. We've spent quite a bit of time looking at the key difference between A-level computer science and GCSE computer science when it comes to Boolean logic. And I've also introduced you to some new terms as well, such as being able to illustrate, derive and simplify. That tends to be the language that we use at A-level. What I'm going to do in the next part of this video is to revise the basic logic gates from GCSE. I'm going to introduce you to the exclusive OR gate, and then we're going to look at some basic primitive Boolean expressions which allow us to describe logic gates and their truth tables using maths. So we'll see you in the next part of the video. So in this part of the video we're going to go right back to GCSE and we're going to revise the 3 logic gates and the truth tables for those logic gates, which of course you remember are the NOT gate, okay, the NOT gate, the AND gate, and the OR gate. Those were the three that you needed to know at GCSE level computer science. And of course, guys, these don't go away. Let me just turn off the lights on my, see if I can get those right. There we go, that's better. Yeah, and of course there are associated truth tables with each of these. I'm going to use the different type of terminology and vocabulary which I mentioned in the first part of the video. So what we would say is that when we draw a NOT gate, for example, and also we complete a truth table, what we're doing here is we are illustrating a type of Boolean logic using this type of symbol, okay, the NOT gate, and from the NOT gate we can derive a truth table, and likewise from a truth table we can derive our NOT gate. In this particular case, both of these are pictorial illustrations of Boolean logic, and of course with the gate symbol this is doubly useful for us because of course this symbol or symbolism forms the basis of schematics for manufacturing digital circuits. A little bit later on in the video we're going to look at the way in which we express Boolean logic mathematically as well. For the moment though, let's just go back to GCSE and revise the gates and the truth tables for our three types of gates that we needed to know at GCSE. We're going to start off with the NOT gate. Okay, so the NOT gate's very simple. A single input, a triangle with a circle at the end. Very important to remember the circle, because if you forget circle, then in actual fact you're representing a different type of component. So it's very important to remember the circle. I'm going to put A as our single input and Q as our output. And let's draw our very simple truth table for the NOT gate. We've only got two columns, one for the input and one for Q, the output. We only have two combinations of A, which is either going to be a 1 or a 0. So if A is 0, we get Q of 1 on the output, and if A is 1, we get 0 on the output. So there are a number of ways of expressing this. We can say that Q is the negative of A, is not A. We can say that Q is A inverted. An even better way to express this is to simply say that Q is not A. And we'll look at the way that we can express that using mathematics a little bit later on. So essentially Q is not A. Okay, so that was a simple one because that's the NOT gate. So let's look at the AND gate, which I'm sure you guys will remember is the giant D. Okay, so let's draw our giant D. This time of course we've got two inputs to our AND gate. I'm going to label these with A and B, and I'm going to stick with Q for the output. Okay, here's our AND gate. Let's draw or derive the truth table from our illustration using the logic gate symbol. So on this occasion, I'm not going to have enough room there, am I? Let's draw it a little bit bigger. So this occasion I'm going to have three columns. Okay, for the two inputs and the outputs we're going to have A, B and Q. This time of course I'm going to have four possible combinations of zeros and ones. So let's make sure that we can do that in our table. We're going to use a slightly different colour here. So let's simply count up in binary 0, 0, 0, 1, 1, 0, 1, 1, and let's look and revise the output. So I'm sure you guys remember that with an AND gate we will always have 0 output unless we have this single condition here, which is a 1 for both A and B, and that's the only time that we get a 1 for our output is when A and B are both 1. Okay, so that's the AND gate illustration of Boolean logic. Let's have a look at the last one, which is the OR gate, typically the hardest one to draw. And whilst I'm busy drawing this, just as an aside, I will be putting a video together, if it's not there already on the playlist, which is to give a general advice, particularly for exams, about hints and tips that you guys can pick up for your exams and indeed classwork as well. One of which is to make sure that you draw these diagrams so that there's no ambiguity between them. So with our OR gate, what I tend to do to make sure that my OR gate doesn't look like an AND gate, which is very easy to do in the heat of an exam, is to make sure that I exaggerate the curves of the OR gate symbol. So I'm going to put a nice big curve in, a nice curve there, and a nice curve there. So there's no way that that can be mistaken for an AND gate. Let's draw the truth table for our OR gate. And our OR gate, same structure. Okay, we're going to have 3 columns for A, B and Q. A, B and Q. Again, we're going to have 4 possible combinations for 0 and 1. Okay, because we've got 2 inputs. So let's put those down. Let's count up in binary: 0, 0, 0, 1, 1, 0, 1, 1. And with the case of an OR gate, I'm sure you guys can remember, we will always get a 1 on the output, with the exception of A and B being 0. Now for an OR gate, we'll just write that here. There are a number of different ways that we can express what's going on here in English. We can say, for example, that with an OR gate we get Q of value 1 if A or B or A and B are 1. Okay, A or B, A and B equals 1. In other words, one or the other or both will give us a 1 on the output. So that is the illustration using an OR gate and a truth table for this particular type of Boolean logic. Now, you remember earlier I said that at A level we need to extend the learning from GCSE to include a 4th gate, which is the exclusive OR. So what I'm going to do actually is, I'm not going to have enough room here, so I'm going to leave the OR gate on the whiteboard, and I'm just going to draw a smaller version. Let's see how far up I can go. There we go. I'm just going to draw a smaller version of the truth table at the top here, so we can make a direct comparison between the OR gate and the exclusive OR gate. So hopefully I haven't made this too small. Let's divide this into 3, and let's divvy up the rest of the table into 4. Let's put our inputs A, B and Q at the top. Let's do our counting up. So we have 0, 0, 0, 1, sorry, 0, 0, 0, 1, 1, 0, 1, 1, and we said with an OR gates that we always get 1 on the outputs unless we have nothing at all on the inputs. So let's represent that with a different colour like this. Okay, so before we draw the exclusive OR, I'll just draw your attention to the bottom combination where we have both A and B of 1. So remember with an OR gate we said that A is either, sorry, to get a Q of 1 it's A or B or both A and B having a value of 1. So let's compare that with the exclusive OR gate. So I'm going to draw the exclusive OR gate underneath. It's almost the same symbol, in fact. Okay, so it's basically an OR gate as was, but we need to remember with an exclusive OR gate to put an extra curve at the front there. So A and B and Q, and this is the exclusive OR gate. So the only difference visually is this additional curve that we have at the front of the gate. So you need to remember to include that if you're planning on illustrating an exclusive OR logic. So let's put the table down here for an exclusive OR. So let me just label this up with OR. I'm not going to see it there, so let's pop it here. This is our OR, okay, and this one is our exclusive OR truth table. Okay, so let's divvy this up as before. Okay, 3 columns. This. Okay, we're going to have to divvy this up into 4 as well. Right, let's pop in the top A, B and Q for our output. Now on this occasion we are going to get, let's just pop in our various values for A and B, 0, 1, 1, 0, 1, 1. So with the exclusive OR, unlike the OR gate, we are only going to get values of 1, okay, when A and B are exclusively 0, 1 and 1, 0. In other words, A and B are not the same to generate a value of 1. All other combinations, or our other 2 combinations, will give us 0. So the way to express this is to say that an exclusive OR, to get a value of 1 for Q, it's A or B, but not both. Okay, not both. Alright, so make a direct comparison here between the exclusive OR and the OR gate. With an OR gate, A and B is one or the other or both can be 1 to generate a 1 on the output Q, but with an exclusive OR it's one or the other but not both, will give us one on the output. Okay, so an exclusive OR focuses exclusively on when it's A or B and excludes the possibility of A and B being equal. Now there are lots of occasions in digital electronics and that aspect of computer science where we need to be able to create circuits to do exactly that, but also in programming as well, because in Python we have the ability to express an exclusive OR condition, because there are occasions where we specifically want to compare one condition with the other condition, but not to have both true as being inclusive for that particular condition to be true. Okay, so we've covered off all three of our GCSE gates. We've included our extra gates for A-level. I need to talk to you guys about NAND gates and NOT gates, but I'm going to leave that until a little bit later on, because I want to express those particular combinations of gates using Boolean maths. So let's have a look at what Boolean maths, or the Boolean mathematical representation of logic, looks like. So I'm going to rub these out. So we're going to go back to the NOT gate, and this time we're going to express Boolean logic using some maths and some symbols. So you'll remember in the first part of the video we talked about the different language that's typically used at A-level, and we said that when we draw a logic gate and a truth table, these are illustrations of Boolean logic. What we're going to do now is we're going to express Boolean logic in its simplest form, and its simplest form are essentially the four logic gates, but we're going to use mathematical conventions or mathematical symbols. So we're going to start off by looking at the NOT gate again. So let's draw the NOT gate. I won't do the truth table, okay, because we can avoid that for the moment. And let's have our inputs A and our Q. Now you remember in an earlier part of the video I said that essentially Q is not A. Okay, so when A is 0, Q is 1, that's not A. So it would be nice if we could have a mathematical way of expressing that logic without necessarily writing down a truth table, and we can, because we will say that Q is identical to or logically equivalent to not A. Now this particular symbol doesn't have a special name, it's just called the, sorry, let me just move this over for you guys, equals not A. So this symbol, which is the straight line with the drop down at the end, it's on your keyboard, top left hand corner, doesn't have a particular name, it's simply called the not, or the negative sign, okay, or symbol. So Q is logically equivalent or identical to not A, using this particular symbol in maths. Let's look at the way that we express the logic for an AND gate. So let's rub this out. I'm going to summarize these towards the end of this part of the video. So we're going to draw an AND gate. This time, of course, we have our two inputs A and B. Let's draw our giant D for an AND gate. Okay, there we go, with output Q. And to express this mathematically, we would say that Q is identical to or logically equivalent to A and B. And you can see that the symbol that I use to express AND logic is the caret symbol, okay, C-A-R-E-T. We just tend to call it the upward arrow, or simply the AND symbol. So A and B represented using this symbol. Let's have a look at the one that we use for an OR gate. So I'm going to draw an OR gate. So here's our OR gate, A and B. Let's do my exaggerated curves to make sure that there is no doubt that this is an OR gate, not an AND gate. We've got Q for the output. Now to express this mathematically, we'll say that Q is logically equivalent to or identical to A. And then for an OR gate, we have the V symbol. Okay, so it's the opposite of the AND symbol. It's a V symbol, or a downward arrow. So Q is logically equivalent to A or B in this particular case. The one that we now need to look at, the last one, of course, is the exclusive OR. And I'm going to cheat here because I'm just going to put an extra curve at the front to change this to an exclusive OR. And to express this type of logic, we just draw a line underneath the V for an OR logic. So this becomes exclusive OR, and we need to make sure that we put a line underneath the V to express this particular exclusive type of logic. So let's just summarize these. We've got 4 symbols, and we're just going to summarize these now. The first one is the 3 bars. So I think in maths, people tend to say is identical to. In computer science, we tend to say logically equivalent. Right? That's the expression that most of us use, is logically equivalent to. Okay, then we had the not symbol, which is the line with the drop down. So this is what we use for not. I'm just going to number these. Number 2. Number 3, we have the symbol for an and. Okay, it's the symbol for and. It's the caret symbol or the upward arrow. And then finally, we have the or symbol, which is the downward arrow. And then finally, this time, we have the exclusive or, and the symbol for an exclusive or is the same as an or, but we need to make sure that we put a line underneath. Okay, now there are different symbols used in different parts of computing and engineering to essentially express the same thing. I'm going to leave those alternative symbols until a later video, and I will probably put them in a video which offers up guidance and advice about tackling questions and using these types of symbols in an exam, because actually it can be very easy to lose marks by virtue of the way that you draw these, the gates, and also making typical mistakes when we come to do Boolean algebra. More on that a little bit later on, but there are alternative symbols that are used, and I just want to make you aware of what they are for when you're doing your own background reading and research on the internet as well. So let's take this Boolean logic and the mathematics to express Boolean logic. Let's take this a stage further, because you'll remember that I said that you guys need to be aware of inverted gates, such as the NAND gate and the NOT gate. So we're going to do that now, and I'm going to draw those out, but we're going to express the logic of NAND and NOT gates using this type of mathematics which we have just come across. So let me draw out what is essentially a NAND gate. Okay, now you're not going to be asked in the exam exclusive questions about NAND and NOR gates, okay, but you do need to be aware of them. So let's draw the logic gate for a NAND gate. So we start off with an AND, okay, and our giant D, A and B. Okay, now a NAND gate, this is a NAND gate, and excuse me, a NAND gate simply means we take a traditional AND gate and we negate the output using a NOT gate, okay, to give us a Q. So this is when it becomes a NAND gate. It literally means not a NAND gate. Now we can draw the truth table simply by adding in an extra column and flipping over what would have been Q there. We simply flip it over to represent our new output. And I'm not going to draw a truth table for this. What I am going to do, however, is to express this combination of gates using the mathematical expressions and symbols that you saw a little bit earlier on. So let me just write that a little bit lower so that you can see it on the screen. So we have an AND gate, and then at the end here is actually an AND gate. So how might we express this combination of gates and combination of logic using our mathematical approach that we saw earlier? Well, what would be the expression for an AND gate on its own? So we would say for an AND gate on its own, Q is logically equivalent to, quite simply, A and B. Okay, so we'd be using the upward arrow symbol to express a basic AND relationship between A and B. What would happen then if we wanted to put a NOT gate on the end? Well, we would simply pop brackets around there to say that essentially this is a single expression, and then we would put our negative symbol on the front. Let me just space that out a little bit. Okay, Q is logically equivalent to not A and B. Okay, note that this is not the same as not A and not B, because essentially in this part of our representation of the Boolean logic, okay, the combination of A and B has already gone through the AND gate. It's after A and B have gone through the AND logic and then inverted that we get our output Q. Okay, So we need to represent that by putting brackets around A and B and saying essentially the whole of this outcome of A and B is then negated at the end of our process, at the end of our gates. Let's have a look at something similar for the NOR gate. So NOR gate is simply an OR gate that's been inverted by adding a NOT gate on the end, just as we have done with the AND gate. Okay, so let's draw a NOR gate. We start off with a traditional OR gate, so we have A and B. Okay, let's draw my exaggerated OR gate with lots of curves. There we go. This time we're going to pop a NOT gate on the end. So essentially, if we call this D as our output of our OR combination of A and B, then here we would get NOT D, and NOT D essentially is our output Q. So to express the OR part of the logic, we would simply say Q is logically equivalent to A or B. So that's the downward arrow symbol. Okay, now to express the fact that our output from the OR combination has then been negated, we simply say that all of that then is negated or inverted using the NOT symbol at the front. Okay, so this is the mathematical way in which we express this type of logic you can see with these two gates. Okay, this is an illustration of a Boolean expression or Boolean logic, and this is the Boolean expression that these gates are illustrating. Excuse me. Now we can have a not exclusive OR gate. I'm not going to go through that because it's exactly the same type of principle with exactly the same type of thinking to express, we'll just move this guys for you, to express our Boolean logic using the mathematics and the symbols. Now before I finish the video, there's just one other aspect of terminology which I want to talk about, because going forward in this unit you'll notice that we start to refer to A and B as variables. Okay, and I'm going to mention it now because I don't want you guys to get confused with different terminology. When we draw logic gates, okay, because it's explicit, we tend to talk about A and B as being our inputs and Q normally as being our output. Okay, but when we start expressing Boolean logic mathematically, we tend to talk about A and B as being variables. They can still be an expression of inputs, but because we are working with maths, we tend to talk about these in terms of variables. All right, just like we would with ordinary algebra with X and Y and other uses of characters to represent expressions, we would also say that X is a variable and Y is a variable, that type of thing. Okay, so in this context, A and B, we talk about them being inputs because it's explicit, but when we're talking about the world of maths and expressing Boolean logic with mathematics, we tend to talk about A and B as variables, and that's just something to bear in mind going forward. So I hope that you found this video useful. There is just one other thing which I wanted to mention right from the outset as we've got this far, and that is just to mention the Logically website and the browser tool. So I'm just going to do that before we finish this video. So those of you I taught for computer science at GCSE will be very familiar with the software, the screenshot of which you can see in the slide. This is Logically. It's browser-based software, it's a browser-based app. It allows you to create drag and drop circuits using logic gates. This is useful at GCSE, but it's even more useful at A-level because it will enable you to be able to build your own simulated flip-flops and adders. And also, when you've gone through the process of doing Boolean algebra and you've created a simplified circuit, you can create those circuits using Logically and test that you've got the correct answer. The browser-based version is free. There is a purchased app which you can download. That gives you the benefits of being able to save the circuits you've created for revision. You may feel that that's a good investment as well, but please do bookmark Logically. It's very, very useful to support your learning and your practice for this particular unit. Okay, so I hope you found this video useful. I'm going to use two phrases now which I know I'm infamous for in the classroom, which is to say, number one, I hope it's helped you to join the dots, and number two, to see the bigger picture. I will see you in the next video of this playlist.